All right, welcome back to Fundamental Theorem of Calculus chapter. It's 6.4 in our calculus books. This is the last video in this chapter, and I want to talk about analyzing antiderivatives graphically. So let's assume we've got some function y equals f of x, and I've drawn a little sketch of the graph of f of x here. All of the points that you see on the graph are completely obvious. And let's define a new function, h of x, which is the integral from 1 to x of f of t dt. So if I want to think of this, this function, I'm starting right here, and I'm adding up these areas until I get to some point x, and then I stop. So let's think about what we can determine about this new function using this graph of f of x. So we'll start with a couple quick questions. First of all, what is h of 1? Well, h of 1 is the integral from 1 to 1 of f of t dt. And of course, that means that I don't have any area at all. So this is equal to 0. Second question is h of 0 positive or negative? Well, looking at the graph of f, here's what I see. I see that f is above the axis, but since I am integrating from 1 to 0, remember, looking back at my function, I'm starting at 1 and I'm going to some value of x. That means I am integrating to the left, and that means that it must be less than 0. A positive integral moving in the opposite direction gives me a negative value. So let's look at the maximum value of h. So what do I know about h? Well, thing one, I know that h starts right here. I think I'll switch to blue. H starts right here, and it goes up, 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 until it gets to here, at which point it starts going down, 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 until it gets to right here. So my maximum value of h, and I also remember that it is negative as I move to the left, my maximum value of h must be right there. My maximum value of h is at x equals 4. Next question, my minimum h. Now remember, I've said value a couple times there. We're not really talking about values. We're talking about what is x equal to, because we don't know the value because we don't have any information as far as how big these areas are. We only have the visual. So where is it at a maximum? It's a maximum at x equals 4 because it stops going up and then starts going down. All right, minimum. Well, I know that if I move to the left here, I'm going to have some little tiny negative number. So it could be a minimum right there at x equals 0. So maybe at x equals 0, we know that h of 0 is some negative. And we know that it is a maximum value positive at x equals 4. But then it starts going down all throughout this shaded red area. And it is quite clear that this shaded red area is larger than the shaded blue. And since shaded red is greater than shaded blue, that tells me that I am going to have passed 0 and be gone down into the negatives, and I'm going to go a long way into the negatives. The shaded red is significantly larger than the shaded blue, and much larger, even the combination is much larger than that little tiny green area. So my minimum has to be when the function gets to the end of the negatives at x equals 8. There's my minimum. So it went up until it got to x equals 4, then it started going back down again. That gives me a maximum, and it keeps going down until x equals 8, and clearly it is a minimum. Finally, last question would be, where are all the inflection points of h of x? Well, let's think about how I find an inflection point. I take the second derivative of a function and I set it equal to 0. And if it changes, then that's an inflection point. If it changes from positive to negative, that's an inflection point. So let's start with the first derivative. Well, the fundamental theorem of calculus says that the first derivative of that is just the function. The second derivative, therefore, must be the derivative of the function, and I want to know where the original function has a derivative of 0. Well, I see 3 places, which I will highlight in gold here. I see the function having a derivative of 0 right there at x equals 1. I see it having a derivative at x equals 3. And I see it having a derivative of 0 at x equals 6. And now let's make sure that it's changing. Notice it was going down over here. It's going up over here. That's an inflection point at x equals 1. It is going up over here and down over here. So there's an inflection point at 3. It changed from up to down. And it's going down right there, and it switches to up right there. So there's another inflection point. I have 3 inflection points at x equals 1, x equals 3, and x equals 6. Inflection points of h of x, which is defined as the integral. So useful things to remember: if h of x is an integral, then the derivative of h of x is just the function, which means that the second derivative of h of x is the derivative of the function. And of course, I can just look at a graph and I can tell, hey, look, the derivative, that's going up, that's going down. And so that gives me my second derivative of the initial function. All right, there is a quick example. Thanks for watching. Hope you learned something. And I'll have my students do exercise 57 in the book.